All right, this video is about the primitive element theorem. All right, so let me just state the theorem. So again, this is the primitive element theorem. Okay, so let F be an infinite field. So the proof I'm going to give is for infinite fields. You don't need this, right? And let L equal f alpha 1 through f alpha n, where alpha 1 through alpha n are elements of some algebraic closure of F. If you're uncomfortable with algebraic closures, just take some algebraic extension and adjoin some elements. Okay, so the theorem is that, so we just take some random extension where we just adjoin some elements. So the theorem is there always exists some gamma an element of L such that this big extension, right, L is just F adjoin gamma. So this extension is basic, or it's some people call it simple, or it's primitive. So this gamma here is the primitive element. It's the primitive element. Okay, let me make a little bit of remark. So what gamma works? Okay, so what gamma works when we do this? So the remark is that, and we'll see this in the course of the proof, 99% of the time, or I should maybe say 100% of the time, gamma, if I take gamma to be alpha 1 plus alpha 2 plus alpha n, if I just take the sum of them, this will work. So I will explain so we explain what this means in the proof. So I'll explain what 99% of the time works. What 99% of the time means. What this means in the proof. And previously, so the previous example that we gave of this was this square root of 2 plus square root of 3 thing. So square root of 2 is square root of 3. And there's a whole video about square root of 2 and square root of 3. And we proved this explicitly in this example. And now I'm going to do the proof in general. Okay, so see that video if you want to see this worked out in an example without using this big theorem. All right, so the proof idea is, so the proof, okay, so let me just say there's kind of some easy parts, but the proof reduces by induction to the case n is equal to 2. N is equal to 2. So like the two-element case like we have here. And I think that I give this at the end of my notes. But no, I don't think I will. So I'm just going to leave this as an exercise. So this part, I mean, yeah. So it's not the hardest exercise, but it'll just waste some time. Okay, so to the case n is equal to 2, where you have two elements, and that the two element one will be generated by many elements. Okay, so okay, so I need some preliminaries actually. So before getting into this, let me I got ahead of myself. Let me just say let me just put this on pause for a second and talk about what things we need. Okay, so let's do the preliminaries before we do the proof. Okay, so I just want you to recall that for alpha. So for alpha in F bar, so an algebraic element, so this M alpha, so this is here, the minimal polynomial. I'm going to use this, has the property that if f of x is a polynomial and it vanishes at alpha, then this means that m alpha of x divides this polynomial. Okay, so that's what the minimal polynomial was. It's an irreducible polynomial that has the property that if a polynomial vanishes at it, then it vanishes at alpha, then this m alpha needs to be a factor. Okay, now I'm going to use this in a lemma, so I'm going to give kind of one lemma and a fact, and then the fact we'll kind of punt to for later. All right, and so the lemma says the following. So it says that if, let's say, f of x and h of x are polynomials, then you can compute the GCD. Okay, so the GCD is really an element up to a unit, but I'm just going to write it like this anyway. So h of x is equal to the GCD of, so the GCD is only well defined up to like a generator of an ideal. All right, so, but I'm going to write it like this. So the GCD of elements in this polynomial ring, so we have two polynomial rings. Notice the difference between these two things. There's this polynomial ring and there's this polynomial ring. And it says that the GCD here, where we don't take the algebraic closure, is the same thing as the GCD where we do take the algebraic closure. All right, that's the point. All right, and so let's prove this. So proof, and this is going to use this minimal polynomial thing. Okay, so let's write. So let's factor it. So write f of x. So this is going to be the GCD. And then we'll write h of x is g of x, h tilde of x. So this, and this is going to happen in f of x, where g of x is a GCD. All right. So now we're going to derive a contradiction. So suppose that, say, f of x and h of x have a common factor. So suppose these tilde versions have a common factor. So have a common factor. All right, so suppose they're not co-prime, i.e., so this means that there exists some alpha in f bar such that f tilde of alpha is equal to 0 and h tilde of alpha is equal to 0. That's equivalent to having a common factor because over an algebraically closed field, those polynomials factor into these monic pieces. Okay, so if this is the case, right, now we get to apply what we talked about here. All right, so that means, this means there exists. So this means that so these guys, f tilde of x and h tilde of x, are divisible by alpha. So m alpha of x divides. So this thing divides f tilde of x and m alpha of x divides h tilde of x. Okay? And this is a contradiction, right? So this is a contradiction. Because we can't have some bigger factor, right? Otherwise, this thing here wouldn't be the greatest common factor. We could tack on this m, so we could put on these extra m alpha x's and then move that piece over. We could move that piece over from the f tilde and the h tilde over to the common factor, making it not the greatest thing. Okay, that's our first preliminary thing. So the preliminary thing says factorization of polynomials over this maybe not algebraically closed field is the same thing as factoring over an algebraically closed field, right? And what this really means is that when you factor, it may break up into these pieces, right? So let me just kind of like show you what this means. So what this means is that, you know, if f of x is equal to, let's say, g of x, I don't know, g of x f tilde of x, like this, okay, these things will break up over an algebraically closed field. I don't know, R. Okay, and so these things don't live, you know, these things are not in F. In F, but they're in F bar. And what happens is that when you multiply this whole thing out, so when you multiply this out, so when you're multiplying, let me just, so I keep forgetting that you can't see my gestures. So if you multiply this out, what you get coefficients in F. F coefficients. All right, that's the point. Is that you factor it. It doesn't matter how it factors. This will give you F coefficients. If yeah. So that's all it says. Oh. Whoa. Okay. All right. I mean, okay. Yeah. I mean, especially when you do the if you do the GCD. Oh, well, let's see. Is that what I want? That looks good. Okay. So, all right. So that's the first fact. The second fact that we need. So so now I'm just going to state a fact without proof. Is that okay? So that if F is contained in L, is a finite. So if L is a finite extension, then there are only finitely intermediate fields. Then there are only finitely many intermediate fields. Okay, so what's an intermediate field? So it says the set of oh, I need to pause for a second to add more pages. Okay, added more pages. So there's finitely many intermediate fields. So what does that mean? So this means that so what do I mean by this? It means that the number of K, which is a field, and K is in between L and F. So this is less than infinity. Okay, and so this is just like saying that the lattice of subgroups. So this is just like saying that the lattice of subgroups of a group is finite. So you only have, so in a finite group, there's only finitely many subgroups that you can have. Okay, that's simply because you have every subgroup's generated by a finite number of elements, and there's only a finite number of subsets. This is actually a consequence of that theorem for groups, surprisingly. Okay, so now we did the preliminaries. So the preliminaries were this factorization business, right? And the fact that there's finitely many intermediate subfields. Those are the two things that we need to do the proof of the primitive element theorem. Okay, so the proof, as I said before, reduces by induction. So the proof when we had L, which was F adjoins some variables, alpha n, to the case n is equal to 2. Okay, so we will write, and I'm not going to work those details out. So we will write here L is equal to f of alpha beta. Okay, all right. So this is what we'll look at, and now we're going to want to show that this thing is generated by a single element. That this is a primitive element. Okay, so here's what we're going to do. We're going to build an infinite number of intermediate extensions. This is where the infiniteness of the field is going to come in. And then we're going to show that there's so many of them that two of them have to be the same. Okay? And using that two of them have to be the same, we will we will get to conclude the result. Okay? And so for each element of our field, of which there are infinitely many, we can take a linear combination of, we have an element gamma of C, which is alpha plus C beta. Okay, so this is an element of L. And we also have the intermediate fields. This intermediate field, L of C, which we'll define to be f of gamma of C. Infinitely many of them. Okay, now, so we have, so this thing here, this thing lives in between L, and it contains F. Okay, so this is L of C, it's in between these two things. So, if all, so I said that there's infinitely many, but we really don't know that there's infinitely many. If all of the LC were distinct, this would contradict the finiteness of the number of intermediate extensions. The finiteness. So the fact that I said at the beginning of the set of K's, which is a field, and K is in between F and L. Okay, so hence there must exist some C1 and 2. Hence, so there exists some C1 not equal to C2, both not equal to 0. Both not equal to 0, such that the two fields are the same. So such that, let's just call it K, L of C1 is equal to L of C2 is equal to, so this is equal to K. Okay? So, all right. And so, all right, and I'm just calling it K for fun. All right, so this is what we have. So this thing by definition is F adjoin alpha plus C2 of beta, and this is F adjoin alpha plus C1 of beta. Okay, so this means in turn that we have the following, that alpha plus C2 of beta must be an element of this field. Okay, that's all right. So, all right. So hence, we could do some equations, right? So so C1 is an element of F, so I can take that times this element, the one that I just did above, and I can do this thing, alpha plus C1 of beta, right? And then this thing becomes C1 of alpha minus C2 of alpha, and then they just cancel, right? And that's all you get. Okay, so this shows that this is in K. And since C1 is not equal to C2, right, this proves that alpha is in K. Right? And by computation, right, so then this also proves that beta is in K. Okay, so here let me just say that so this we know that we have alpha plus C2 beta minus alpha so alpha was in there, divided by C2, this is beta. So the subtracting alpha is a valid operation because we proved it at this stage. And then since we proved it at this stage, and then since C2 is an element of F, we can divide any element of the field to get an element of the field, and then we know that's actually beta that we were left over with. All right, so that shows that, so this shows that here, since we have alpha and beta, that L, which is F alpha beta, this is contained in K. And we had that K was contained in L. This is essentially for free. It was one of these intermediate things. And so this implies, this proves that K is equal to L. And since K is a primitive extension, and we can use alpha, we can use C1 or C2, we are done. Okay, so the issue, so that concludes the proof. But one of the issues is like, what is C1, right? So I said that I would do it in the course of the proof. I would show you that generically, if you take C1 is equal to 1, it should work. Let me just say how to get that constant out. Okay, so let me just say a little bit about what the constants work. So let me give the second proof of this. So let's do the constructive part. Okay, so what we're going to do is we're going to let gamma be alpha plus C beta for some unknown C. Okay, and then we're going to let M alpha, M beta, so these be the minimal polynomials. All right, and so the minimal polynomials for alpha and beta. So then, so note that we have that M alpha of gamma minus Cx. So this is some polynomial f of x, and it has coefficients in gamma, and so it's a polynomial. If we were to write this out with coefficients in this field where we adjoin gamma. Okay. And it has so this thing has beta as a root. Okay, so what's going on here is that we have this extra term here, right? And if I plugged in beta into here, so gamma minus C beta, well, this is alpha plus C beta minus C beta, which is just alpha. And so since this is the minimal polynomial for alpha, that thing's going to be 0. Okay? So, all right, so we have this polynomial. Okay, so now I'm going to do the GCD thing. I'm going to use the other part of what I needed here. So the main claim that we have is that the GCD over f gamma of x of this f of x and m beta of x. So this is a polynomial with root beta is x minus beta, right? Okay, what does this claim do for us? Okay, so this claim proves that, well, beta is in f gamma, since we did the factorization over f gamma, which implies that alpha is in f gamma, which implies that f gamma, so this is the second proof, is equal to f alpha beta. Okay, so what we're doing is we're going to, so what's the strategy? The strategy is to use gamma and the two minimal polynomials, and then use factorization to conclude that this beta must be in this field, right? So it's a kind of a sneaky proof, right? So we're using this factorization property to peel off a term where we know the coefficients, right? That's kind of a really cool idea. Okay, so let's execute this claim, and then in the course of doing this, we'll figure out what the constant c is allowed in this proof. Okay, so what we'll do is we're going to now k is going to be different, so let k be a field that splits both f of x and m beta. So I think k is equal to f bar works. So splits means, and I'm going to say this again later in another video, but splits means that it just factors into monic irreducible pieces. And that's a thing called the splitting field. And we're going to talk about that in like the next video. Okay? So, all right, so I should have just said algebraically, let's just take the algebraic closure, right? So since the GCD of this thing, if I take this one, so the GCD will be the same. Another thing is that the algebraic closure of f is the same thing as the algebraic closure of any finite extension of f. That's because this thing will be contained, it's algebraic, so it has to be contained in the algebraic closure. So that's the same thing as the GCD over here, over this field. Okay, and it suffices, so it suffices to show that the GCD of over the algebraically closed field, so this is x minus beta as we wanted. All right. So what we'll do is we're just going to like compute. So the idea then is just we just compute. So now we just compute. Compute / write out formulas. So that's what I mean by compute. I mean we just write down formulas and this will work out. Okay? So let's write down formulas. Right? So this is x minus alpha 1, x minus alpha 2, x minus alpha some degree d, and here we're using the convention that alpha 1 is alpha. Okay? Similarly, f of x, well, so what do we have? F of x was this shifted version of m alpha, right? So this is what here is how we defined it, right? And so we just take the polynomial for m alpha and then we plug this in. Okay, so this tells us that that we have. Okay, now I plug in everywhere for x. I do gamma minus cx minus alpha 1, gamma minus cx minus alpha 2, dot, 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 gamma minus cx minus alpha d. Okay, and we can figure out what the roots are. So we compute what the roots are. Let's compute the roots. So one of these terms, this is 0, if and only if. So we're supposing Cj is not, this c is not equal to 0. Alpha j minus gamma divided by c is x. Okay, and now we can figure out what this thing is. So here, so this thing is alpha j minus. Okay, now we have alpha 1 minus c beta. All right, so now I'm just applying the definition of gamma, or I guess a plus c beta here, plus c beta. So that's the definition of this. And okay, and so this thing's divided by c, and this is equal to alpha j minus alpha 1 divided by c minus beta. All right, so this is we computed half of it, right? So we computed what the roots of m alpha were. The roots of m alpha look like this. Okay, alpha 1 is again, we're using the alpha 1 is alpha. Next step, let's compute the roots of m beta. Well, we just write them out. M beta is x minus beta 1, x minus beta 2, x minus beta e. E is some integer. And here we're using the convention that beta 1 is beta. All right? And so now if we have a common factor, then for some, so what are we looking at? We're looking at common factors of f of x and m beta of x. And now we computed all of their things. So if they have a common factor, they have a common root. And if they have a common root, these monic polynomials are this. So common factors mean common roots. So this means that beta I, for I not equal to 1, is equal to alpha j minus alpha 1. Here we go. Alpha j minus alpha 1 divided by c minus beta 1. So beta is beta 1. Okay? So this implies that beta I plus beta 1 is equal to alpha j minus alpha 1 divided by c, which implies that c is equal to, so alpha j minus alpha 1 divided by beta I plus beta 1. All right? And so these here, so this gives us a forbidden list. So finitely many. So this is the forbidden, so the forbidden C. Okay? So as long as C isn't one of these things, then we can't have a common factor. Right? So if C is not one of these, there will be no common factor. Okay? All right. And yeah, so these are the C's that we have to avoid. There's finitely many of them. And so pretty much every C will work, and most of the time when C is equal to 1, it will work. All right. So that's all right. So I just want to add one little thing. I don't think I explained this well. So so here we're trying not to have extra factors, right? If we have a common factor other than beta 1, right? So when j is equal to 1 here, this crap goes away, so this is 0. And then this factor will be this. And so this should be a plus here. All right.